Welcome, everybody. To this lesson of the PUM Solar Group. My name is Martijn Schootstra, and I will be talking today about the sizing of PV systems and the economical aspects. First of all, I will be talking about the grid-tied solar system, so systems without batteries. And then we'll be covering off-grid solar systems and backup systems. I also will be talking about an online sizing tool, PVGIS, which you can use yourself to verify and calculate your own situation. Well, to give you straight away the summary of the next lesson, I can tell you that grid-tied solar systems for the Northern Cape are a very good financial investment. And of course, reduce CO2 emissions. Payback times of less than 5 years are feasible. Of course, that depends on how much you pay currently for your utility provider, Eskom. But in general, I could say this looks very positive. I also recommend that you have a solar system that is not too big, and that means that you can actually use all the energy you're generating for direct self-consumption by your own loads. If you obtain quotations from suppliers, then my recommendation would be to compare the cost per watt peak in order to compare between these various quotations. The economics for backup systems or off-grid systems are quite more difficult, and it's not so easy to give a generic answer. It depends very much on the capacity of the batteries that are required. The batteries are expensive, and we want to keep the size to the minimum if possible. It also matters if your energy demand is during daytime or during nighttime. If you have a generator, it matters how many hours this generator is being used. In general, we can say that solar becomes competitive when you can use the energy every day. Now, the good news is that we at PUM, our experts, can help you with your specific situation. Okay, let's first have a look at the sizing of grid-tied solar PV systems. So these are systems, solar systems connected to the grid. Here on this picture you see a sort of schematic. On the left-hand side we see the solar modules, the PV modules or PV array. And these modules are generating DC current. And a grid inverter, a solar grid inverter, is converting this DC power into AC power to a voltage that is slightly above the voltage from the utility grid. And so it's connected to the main distribution board in your office, factory or house. And of course this distribution board is also connected to the electricity grid. Now what happens that during daytime, when the solar installation is functioning, the energy is flowing directly to your loads, depending what loads these are. It can be, say, home equipment, but it could be your factory equipment. So if you generate this solar energy, what you're then effectively doing, then you don't have to purchase as much power from the grid, from your utility provider. So what you're doing, you're actually reducing your purchase of your bill. So we call this self-consumption. So we are lowering electricity purchase from the grid, and the electricity is for direct self-use. Now, if there's no load, then the electricity would go back to the grid, if that is allowed. And it also depends if you are then paid for this electricity that is supplied by the grid. We call that feed-in tariff, or sometimes it's called net metering. Now, as you can see, there are no batteries in this system, so there's no backup. That means that during nighttime, there's no power at all. And in general, when the grid goes down, even the PV generation goes down. There are some exceptions, but in general, this is not a backup system. Now you can say, why do we do this? Well, I would claim that over 95% of all solar systems globally have this setup, so no batteries. And here you can see, no matter if it is rooftop systems or solar farms, they're all connected to the grid, and all with the aim to either have a financial return or at the same time reduce CO2 emissions. Now, if we talk about self-consumption, then maybe it's good to show you this picture. So you see here the orange line is, say, a fictitious load profile. So you see the load fluctuating somewhat during the day and going down towards the evening. And the green line, you see the bell curve, I would say, generating solar energy during daytime, so a bit lower in the morning and the peak around noon, and then reducing again in the afternoon. Now, the area that is now in blue have indicated their self-consumption. There you see that all the solar energy that is generated at that time is going directly to your own loads. And that means that you don't have to buy that the power yourself. You also can see that towards the end of the day, the solar generating is reducing, and that you will have to purchase power from the grid. Now the dark green side, that means that is surplus energy that you cannot use directly at the time. And since there are no batteries, that power can be fed back into the grid. Again, providing that's allowed. If not, and we will see that later on, then a system with batteries might be beneficial. So also we can say here, this system is maybe too big. My recommendation would be to have a solar system that is slightly smaller, so that you can make sure that almost all the energy generated by the solar system is being used directly in your own system. Now, then you can ask me, so, well, how many solar panels do I need actually? Well, that of course, as we saw in the last graph, depends on your electricity consumption. It starts always, the design of the system is looking at your consumption, and usually the energy bill is a good basis to start off with. So I would call that's a constraint. And as mentioned, if net metering and feed-in is not allowed, of course, that changes the situation somewhat. But if it is allowed and if the tariffs are good, that will help your financial return on such an investment. There are other constraints for a solar system. And one aspect is, of course, how much space do you have available, either on the field or on your roof. Also important is the roof capable of taking the extra weight from these solar modules. Another constraint might be the capacity of your grid connection, and that's in particular when you are supplying back to the grid. And lastly, but not least, a constraint usually is the available budget. Now, the advantage of solar systems are that you don't have to purchase a full system if your budget is limited, you can start with a smaller system. And if you're happy, then in 5 years' time, you can add another system, a separate system, or increase the capacity of the system. So out of these four constraints, you get actually, say, the lowest number, and that will define the capacity of your solar system. And we call that in kilowatt peak or watt peak. And that also means that that is the investment you would have to make for such a system. Now, depending on the size of the PV modules, you get a certain quantity of modules. Later on, I will be talking about an example with, say, 20 modules of 320 watt peak each. That means 6.4 kilowatt peak system. Now, if you know the orientation of this of the solar array, all these modules together, we can actually then predict how much electricity will be generated by this system. And we will be using the program called PVGIS. Now, depending on how much you pay currently for your electricity, that will define how much savings you're making. Remember, we're generating solar energy, and you are using that directly yourself, and therefore you don't have to purchase that much energy from the grid. So on one hand, there is an expenditure, the capex, and on the other hand, you have savings every month, every year, and together we can calculate payback time or return on investment. I will come back to this later. Okay, well, now what's happening? We have we have the sun as our energy source, and the sun intensity depends very much on the location where you are on the Earth. The closer to the equator, there is more energy than further north or further south. But it also depends on the weather. I mean, how many clouds is there, and seasonality. So there could be in wintertime you could have reduced solar energy if the sun is on the other part of the hemisphere. The solar system will convert this solar energy into electrical power, and it matters how these modules are positioned towards the sun, and we call that tilt or slope and the azimuth, and of course, as mentioned, the total size of the system. Here you see a small drawing with the tilt angle or slope, and that is the angle between the horizontal and the solar modules. And the azimuth is the angle of the orientation of this solar array between the south. Now, in general, we position the solar modules towards the equator. So if you're in the northern hemisphere, the azimuth would be, say, 0, because then you're positioned towards the equator. If you're in the southern hemisphere, like in South Africa, you will be orientating your modules towards the north, towards the equator, and then the azimuth would be minus 180 degrees. There are also some losses in the system. Temperature could be one of them. The higher the temperatures, the efficiency of modules are somewhat lower. And there's some losses in the inverter and in cabling. Shading losses are actually really could be a real problem, and they should be avoided at all cost. There are some technical measures to reduce them. And there can be fouling, and fouling we think of either dust or bird droppings or leaves from trees and so on. Now then, there are some simulation tools available, and there are several online. I mentioned these two in particular. One is called the Global Solar Atlas. If you Google that, you'll find it quite easily. And the other one is PVGIS. I personally like PVGIS a lot. And the reason is that it not only deals with grid-tied solar systems, but also with off-grid systems. And I have not seen any other programs doing that as well as this one. So PVGIS. PVGIS is an online geographical information system for solar systems. And with that, we can predict the amount of electricity a solar PV system is likely to generate. So it's for a specific location. So for your situation, where you are, the database knows the solar irradiation, the temperature, and the weather, i.e. the clouds. And that is done by using satellite data. It works almost globally, at least for most parts of the world. You can see some white areas like southern in Chile and in Australia and so on. It's not functioning, but for most other parts of the world, it works. It's covered. It's a prediction, but people have actually tested this with actual local measurements, not on every city in the world, of course, but on several spots, and have noticed that the tool is accurate within 10%. So this is a fairly good estimate. The web address is a bit tricky, as you can see. If you Google it, you may not find it straight away, but here's the address. And the tool also works on a mobile phone. Now, the methodology is as followed. On one hand, you need to input your data, and the main one, of course, is the location where you are located, and the system capacity. If it's an existing roof, then you know the orientation of this roof, the azimuth, and the angle, the slope of that roof, and you would enter that in the model. As output, the system will tell you the amount of energy that will be generated by that solar system in kilowatt hours on average year. Of course, the weather will change year on year, but it nevertheless gives you a prediction for that average, and including a monthly variability. Now, if it is a new building or it's a field-mounted system and you still have freedom for the azimuth and the slope, the system can also optimize this angle and this azimuth. So that's quite handy. Then at the bottom, you can also see there's some, if you enter the cost of the system, interest rate and the lifespan, the system will also calculate the levelized cost of energy for that particular situation. In this lesson, I will not be dealing with this. Okay, well, I will demonstrate how PVGIS works. So we search on internet the website of the PVGIS, and you will see this screen. If English is not your preferred language, you can select in that box either Italian, Spanish, or French, but the default is English. it's also default is grid connected module. You see a little bit down, so you see there below there tracking PV, and then the third box you see off grid. Later on in this lesson we will using that tab for off grid. The next step, of course, is to enter the location where the project is concerned. Now you can enter the city for that particular location, usually with a comma, and then the country. Then you will make sure you end there. If you cannot find your city, then and you know the coordinates, you can enter the coordinates in the box next to it. What you also can do, you can move the map around and zoom in and drop a pin on that location. So several ways to find your spot. Once you've and then you important to press go, and then in that case the system will jump to that particular location. Now, once you've done that, we then get a bit more detail in the program, as we can see here. The PV technology we can keep at crystalline technology. Most important then, of course, is the capacity of the system you had in mind. Here you can see distilled 1. I usually start off with 1 just to get a feeling for the amount of solar irradiation for that location. Then important is to select here, you have the mounting position, and the system by default goes to freestanding, but I would recommend you to select roof edit or build it integrated. And the reason is that roof edit solar modules, there's a bit less ventilation, and that's why the modules warm up a bit more, and that reduces the system output a little bit. So you're a bit safer. For, of course, field-mounted systems, you can keep it at freestanding, and it will give you a higher output. Now, if you know the slope and the azimuth, you can enter that in a box. And if you don't know that, you can select next to it, you can see optimized slope or optimized slope and azimuth. Now, I discovered that for South Africa, you might help the system a little bit, and I would recommend then say select azimuth minus 180 and tick the box optimize slope. And then you can press visualize results. And the system will then come with this output. Again, at the left-hand side at the top, on the list you see the summary, it says provided inputs, and that is the location, of course, but mainly the size, the capacity of the solar system, in this case 1 kilowatt peak. Below there you see the outputs. On one hand you see the slope angle, and it will, if it is optimized, it will show the optimum and the azimuth angle. And then the most important output of this program is the next one. It's called yearly production, PV production in kilowatt hour. And below that, even you see the variability depending on the weather. So fairly accurate in general. So within 10%, you can expect this to be accurate. Then in the graph next to it, the bar charts, you see the variability during the year. And in this case, in this particular project, you could say the worst case would be during August with the least production, usually during for cloud cover. If there are mountains in nearby, the system will also take that into account. And you can generate a PDF report and store that for later use. Now I've created a sort of a sample project. As I mentioned, we had say 20 modules of 320 watt peak power. So I've added, put that into the system, a system capacity of 6.4 kilowatt peak. And you can see then the output with see the optimum slope angle is 31 degrees. This is for Koruman in Northern Cape, with the azimuth angle at say facing north, and a yearly production of more than 11,000 kilowatt hours. So that's a good performance, I can tell you that. Below there, if you then divide that number by 6.4, you get the specific production of 1,773 kilowatt hours per kilowatt peak, and it's extremely good. In Durban area, it's around 1,400, and here in the Netherlands, it's 1,000, and with still 1,000, it's an attractive proposition, solar energy. On top of that, what is just amazingly good for this region in the Northern Cape is that there is very limited variation during the year. To be honest, fantastic for solar energy. Now, fantastic, okay. Then maybe we also should look at the economical aspects of such a project. As mentioned, we do this for a financial return. So if we take this example of this 6.4 kilowatts system, a kilowatt peak system, grid tied in Koruman, we have a tool. We can help you with that, but my estimation would be that the cost of such a system would be around 110,000 rand, which is around 17 rand per watt peak. I also have based this on a utility tariff that you're paying to Eskom of around 1.9 rand per kilowatt hour. And if we do, then I come to a payback time of around 5 years, an internal rate of return of 18%, which should be well above inflation or interest rates in your country. And you will be, in 20 years' time, nearly tripling the money you invested. Of course, there is also CO2 reduction. So we want to avoid global warming and reduce CO2 reduction. So that should not be forgotten as a main goal. I would say I'd like to verify these numbers with an actual project. Undoubtedly, we will come back to this in more detail. The cash flow, in fact, the cumulative cash flow of the investment looks a bit like this. So you see here on the left-hand side, you see in the year 0 the investment of minus 110,000 rand. And you see that each year you'll be saving on your utility bill, and after 5 years you have repaid or you recovered the initial investment, and after that you will be making a good financial return. The beauty of solar is very low maintenance. You may have to replace the inverter after 10 or 12 years, which is actually indicated here in year 13, you see a little drop. So I've taken that into account as well. In this table, also some numbers for this particular situation. Now, the advantage of solar also is it is very scalable. So if you ask me, but I want a bigger system. Okay, fine. For bigger systems, the numbers will be even better because the cost of the system will be slightly more lower. But for smaller systems, this works as well. And as said, you can start off with a small system and then in the future expand the system or install the second one. Now, what to do? You looked at your electricity consumption, you looked at your energy bill, and you said, okay, let's ask now some suppliers for quotations. And you consult these suppliers, and they send you different quotations, but also for different system sizes. Here, and you don't know what to do. How should I compare this? Here we have an example. I mean, this is in euros, I'm afraid. It's not in rand, but the basics is the same. 3 different suppliers, A, B, C. But as you can see, the capacity of the systems are not the same. So A relatively small system, B is somewhat bigger, and C is almost double the system. And you can see also at the price, the A is the cheapest system, and then it goes up. And so first thought you think, okay, let's go for the cheapest system, which is A. Okay, fair enough. But what I recommend you to do is to calculate the cost per watt peak. And you divide the price by watt peak. I mean, it's indicated there kilowatt peak, so you have to multiply that with 1,000. And if you do that, you get these numbers. And then suddenly you discover that project C, it's highest investment, but it has actually the lowest cost per watt peak. So if all suppliers are good, then I would say, okay, C would be the best bet, providing your budget allows it, of course. And if not, you say, okay, then maybe A is a better option than B. Of course, look also at experience of the suppliers, because quality is important, and aspects like safety, and that not just safety during installation, but also the fire risk. Usually just to say the cheapest is the better, that is not always the case. So we at PUM can help you analyzing these suppliers and quotations. Okay, that was grid-tied solar systems. Now let's have a look at the sizing of off-grid solar systems. That is slightly different. In grid-tied systems, we look at the total year production, and for off-grid solar systems, we need to look at, say, the so-called worst period. And the worst period is usually during the rainy season or during winter time. We need to, of course, on one hand, have sufficient solar panels to generate sufficient amount of energy for our energy needs. And of course, when there is no sun, we need to get energy from an energy source, in this from a battery, either lead acid or lithium batteries. So we need to calculate both of them. So again, it starts with what is actually required. What is your energy demand per day? Maximum energy demand during the worst time of the year. And we do that in kilowatt hour per day, or for small systems in watt hour per day. And we, on the basis, that would be the basis to calculate the sizing of the solar PV. There is a manual method by which we can calculate that. I will not be covering that, but we use PBGIS instead. On the other hand, depending on the hours or days of storage, that will define the size of the battery bank in watt hour, kilowatt hour, of course, amp hour capacity. And we can use the program PVGIS to check if this system will work well. So where do we start? Well, we have to start with a load list. That means you make a list of all the loads you want to power, the power rating in watt or kilowatt of that unit, the amount of hours these loads are operating per day, and thereby you will calculate the energy consumption during the day in kilowatt hour. Also important to know if this power is needed during daytime or nighttime, and preferably if you can switch from nighttime to daytime, that would be even better, because then you don't have to store it all in the battery, and the battery can be smaller. We also need to know the peak load of such a system, because that will define the capacity of the inverter that is required. Now, a load list would look a little bit like this. Here is an example, certain quantity of equipment, the power rating of each unit, and then the number of hours per day these units are operating. Then you see the 24 demand in kilowatt hour. In this case, the total is 24 kilowatt hour. And if you then select day and night, we can also estimate the amount of energy required during daytime and the amount of energy required during nighttime. Now, there are more aspects here. Are the loads seasonal? For instance, during the wintertime, you might not need an air conditioning. So that makes it's better, because during the wintertime, usually there's less sun. So that helps a little bit. Are the loads any critical loads? For instance, you might have a refrigerator for vaccines, for instance. If that's the case, then you do not want any power outage. So in that case, your battery might be bigger. Are there any loads deferrable that you don't need? And also important to keep the cost down is, are there any appliances that are more efficient than you are currently using? Because you will discover that the capex of an off-grid system is much higher. So any savings upfront will have a really important impact on the size of and the investment of this solar system. Okay, now we can then use again PVGIS to help us see if a system would work. So again, that's dependent on your location, because that knows the solar irradiation for your location and the weather. We have defined the energy demand. And in this case, we have to guess somewhat how much solar energy is required, or we use this manual method, which I'm not explaining right now, and the battery capacity that we had in mind in watt hour. So that is amp hour times the voltage. Now, if we put that into PVGIS, the system will tell us the percentage of the days the battery will be empty. So in fact, we call that loss of load. Now, that is maybe not a problem if that means you're watching television and you could say, fine, then I'll do something else that evening. But if we're talking about critical loads like the vaccine freezer, then it's not acceptable. It will also give an indication for the state of charge of the batteries. That's important for lead-acid batteries. So it's not PVGIS is not used for calculating the capacity of the solar array and the battery capacity, but it's more a verification tool. nor is there any optimization of the tilt angle. Nevertheless, the program is very handy, and you can use it in a sort of a trial and error method and adjust capacities accordingly to make sure that the system works well. Well, let me show you how that works in practice. We again go to the website of PVGIS. We have selected the location. First I must say we select off-grid module. That is indicated here, the third tab. We enter the location and press go. And then on the right-hand side, we install the data. We enter the data we had in mind. So the size of the solar array. Please note this is now in watt peak instead of kilowatt peak. So in general, these off-grid systems are a bit smaller. That's why they opted for watt peak. The battery capacity is not in amp hours, but in this case it's in watt hours and not in kilowatt hours. So take care. Then the system wants to know the discharge cutoff limit. I recommend that you enter 50% for lead acid batteries and 20% for lithium batteries. And the daily energy demand, which we have calculated on the load list, you enter in here. And of course, then again, enter the slope and the azimuth of the orientation of the PV modules. So once that is done, you can click Visualize Results. Now here I have an example of just another small system, again for the Northern Cape. Where you see the blue lines, I've added the PV capacity of 350 watt peak, battery capacity of 2400 watt hour. So that could be, out of the top of my head, if it's 24 volt, it is 100 amp hour, or if it is 12 volt, it is a 200 amp hour. The discharge cutoff limit 50% because it was lead acid batteries, and consumption per day 1000 watt hours. That means 1 kilowatt hour per day. The slope angle 35 degrees and the azimuth minus 180, so towards the equator. So now below at the bottom, your simulation output, you see there on the left at the bottom, and with against the red dot you see percentage days with empty battery. Say around 4% of the day. So in my view, this system is not functioning too well. Either you will have to reduce the consumption, the load, or you will probably have to, in this case, increase the capacity of the battery. This is more powerful tool than it will look at first, and I recommend you to try it. Maybe you have a system, you know the capacities, and I would say enter the data and just verify what's happening. Now the economical aspects of off-grid solar systems are again different, and capex is the investment is much higher than grid connected systems, and that is due to the cost of the batteries, but also of the inverters. And therefore, it's very important to reduce your loads and the energy demand and use efficient equipment. It often is much cheaper to invest in a highly efficient equipment than to oversize the capex of this off-grid system. Now, it's not just only the capex, it's also that the batteries have a limited lifetime and need to be replaced. Say lead acid batteries, good batteries can last up to 4 to 5 years. Lithium maybe up to 10 years, but that's an important aspect to consider. Now, if we then look at economics, of course, then we should compare to the alternative. And if it's off-grid, then that means there is no grid. So that's not your alternative. Your alternative is a generator. Now, the generator in general is much lower in terms of initial investment, in terms of capex, but it has much higher operational cost. Of course, diesel, but also maintenance and even overhaul. The lifetime of a generator, if the generator is running every day, is not that long actually. So if we compare the two, we might get a graph something similar to this. You see on the horizontal axis the years and on the vertical axis the cumulative costs. And if you look at the yellow line, you see that's the solar installation, and you see also new batteries being installed every 5 years. That's why you see this step going up. And the black line is the cost of the generator. Much lower capex initially compared to the solar installation. But you see here, in this case, a break-even at around year 14 or 15. Bit too long, maybe. As again, this is an example where maybe solar is not the best alternative for your situation. Now, let me show you again some of the economics in a slightly different manner. And here you see the several different technologies on a vertical axis, and horizontal you see the cost in dollar cents per kilowatt hour in a range. Cost of grid connected solar is below 10 cents in most places in the world now. Prices have reduced a lot over the last, decades, I would say. And for your Northern Cape, as we saw with the grid-tied system, the payback would be less than 5 years. That means grid-connected solar will be well below 10 cents. Utility, you're probably you'll be paying more for utility, so that means that a grid-connected solar system can compete against the utility. And that is particularly for direct self-consumption. Now, we also just saw that the batteries make off-grid solar much more expensive. So if we talk about cost per kilowatt hour, it's a wide range, maybe up. It could be anywhere, depends much on the capacity of the system, the battery storage, and so on. So much more expensive than grid-connected solar systems. But as mentioned, we should be comparing off-grid solar against a generator, and a generator is expensive, and diesel costs are increasing more recently, and we have maintenance costs. So in most cases, I would say off-grid solar can compete with a generator, but it depends very much on your specific situation. So off-grid solar is usually it's more expensive than a utility, but it can be cheaper than a generator. In general, we can say that going off-grid is usually not cost-effective. So if you have the utility, then I would say use that, probably in combination with the backup system, but not pure grid. Pure off-grid is quite expensive. Okay, indeed, if there is load shedding, in like you have in South Africa, or the grid fails and you have suffering from blackouts, then it's important to look at solar backup systems. Now, the sizing of solar backup systems are in some respects similar to off-grid solar systems. So it starts off with the load list, what is required, and so on. But in general, we can have a smaller battery because we only need to cover for a limited amount of time, say 4 to 6 hours, depending on the length of the power outage you have. And of course, we can also decide that we want this backup system only to serve some essential loads and not necessarily everything, or big machinery that we can say, okay, we will not use that during that time. That matters quite a lot in terms of the investment. What also is important is this your consumption, is it during daytime or during nighttime? Again, if there is solar, then we can, and it's grid connected in this case, because we have grid, but with batteries, we will also be reducing utility bill. And again, you should be comparing that against the alternative. The alternative is a generator. Now here I have another situation, again 2 graphs, one for solar, one for the generator. You see in this case, this generator is operating many hours, and the cost of diesel means that you see the steep incline of this curve. And whereas solar actually is going down because you are also saving on your utility bill. And here in this case, you see that the payback time of this solar backup system is well, even less than 4 years. So this is a little bit the case that it depends very much on the specific numbers and in the situation. So it's difficult to give a general remark. In general, we can say a generator might be better than a solar backup system if you only have to use this generator only a few hours per month. But if the generator is running every day, then my bet would be that solar backup system will be has an advantage. Now, we showed earlier this load list with self-consumption. In this case, we have now batteries in the system, and the system becomes slightly different. You see here the blue at the bottom, you see this different load profile, but the solar energy is used for direct self-consumption. And the solar array is generating more power, and you see the green part of this graph, that energy, that amount of solar energy is used for charging the battery. And that energy is being used again during the evening when there is no sun. You see that, and during nighttime, and until the battery is, almost empty. And you see there early in the morning at 2 o'clock, here you see the battery is empty, and the grid will take over the load demand. Now, when you also see here, when the batteries are full and there is surplus solar energy, and depending if that's allowed or not, you can feed that back into the grid. So I thought it might be just to give you some insight on what's happening. Now, I also thought it would be good to give you some indicative numbers for, and we're talking about various technologies. First of all, we started off with grid-tied solar systems, and that's economical. It can compete with the grid. And in the table, you can see it's the first line, backup. It says none, it's grid-tied. It is a solar system with 6 kilowatt peak, no battery, and say the investment is indicated there. Now, as soon as we add batteries to the system, we see that you can see that the cost is increasing. So 2 hours, 4 hours, 8 hours, the investment capex is increasing quite a lot. Now, there's backup system, but if we went purely off-grid, then we need significantly more battery power. And you can see that the investment is also going up quite a lot. Now, again, we need to compare the alternative, and that's the generator. So, as a summary for today's lesson, the economics of backup systems and off-grid solar systems are very much dependent on the specific application at your installation. And batteries are expensive, and we want to reduce this capacity as we can. It depends very much on the frequency and duration of the power outage and load shedding that we want to cover, and only for essential loads. It also matters if you need your energy usually during daytime, and if your generator, how many hours that the generator is currently operating. In general, we can say that solar becomes competitive when it's used daily. So that's something to look into. And as we saw, grid-tied solar systems make a very good financial investment, and of course reduce CO2 emissions. Payback times of less than 5 years are feasible. And my recommendation would be have a system that is not too big to cover direct self-consumption. And if you compare quotations, then look at the cost per watt peak. Now, we at PUM, we can help you further with your project, either online via remote coaching. We could be assisting you, or in person during a mission to your plant. We could help you analyzing your situation and defining your requirements, and calculate a suitable size of PV system and battery capacity. And we could help you in analyzing quotations that were given by local suppliers. So I hope you enjoyed this information, this session, and look forward to hear more from you.